Okay, so today we're going to be focusing on, I know this course is on cross-section, but we're going to talk about panels just a little bit. In the sense we're going to kind of focus on shorter panels for sort of the first parts, and then we're going to shift into some of the things that we find when we're looking at those limited dependent variable models and how we deal with that unobserved heterogeneity. Because a lot of the things that we do, we're always trying, well, I think I've repeated this several times, trying to isolate the impacts of our primary variable. A lot of times I will be mentioning some things in here by saying causal, but I'm saying under those, when I say that, I'm going to be talking about under perfect conditions, okay? If we're thinking about general work, just think of it more that we're trying to mitigate any type of bias or confounders that basically try to isolate the impact as best as possible. Doesn't mean that it's perfect, but at least we're trying to reduce the amount of not being consistent or biased in terms of our primary variables, or the variables of interest in this case. So most of you know some of these data definitions, especially since I found out like a lot of you do a lot of time series. I can tell by the questions I get. In that case, this isn't going to be as pertinent to you, but basically, in terms of data definitions, we basically look at pooled data, are basically cross-sections of data across times, or cross-sections of samples across time. But in pooled, we're thinking about it as being, we can't really follow the unit of analysis. Now, it doesn't mean that we can't follow them, some type of larger type, like an aggregate type identification. So we might be taking regional samples, but we don't know if it's the same individual within each of those samples. So we do have some identification on the region maybe, or some type of, something above what the unit of analysis is. But specifically, the people could be varying, or they could not, because we're not keeping track of them. So we're just unsure whether those units of observation are being resampled. In this case, we can also think about panel data. That's where we're actually following individuals. And it opens up a lot of methods to actually control for things that we can observe. So a lot of times we're adding variables, we're adding controls that are supposed to help us in the overall unobserved outcomes that are sort of ending up in the error term. We're sort of trying to draw them out so that we're more focused, and we have less, it's less likely to be exogenous, or strict exogeneity. So we're going to assume that I represents some unit of observation and T some unit of time. These are some of the most basic ways that we set up panels. For now, we can assume that we have balanced, but I'll go ahead and tell you that most data sets, when they come to panel, it's unlikely to be perfectly balanced. So a lot of times we have unbalanced panels where few of our units kind of go missing, and they might even come back into the sample, but for some reason we stopped observing them. Okay, and this is typically, I'm going to assume for right now that there's not any trouble between these two. A lot of our estimators, we don't have that problem for the most part, or at least we assume it away in some issues. But it's just easier not to deal and just assume that, for right now, we're going to kind of think of these as being mostly balanced. We're going to look at the panel techniques for linear models. We're going to focus on differencing within transformations. I think I can't remember if I put in random effects in there. And And then also I'm going to talk about correlated random effects. The reason why I'm talking about this here is because it is a method of dealing with unobserved heterogeneity in nonlinear models. Okay, one of the problems we have when it comes to nonlinear models or categorical models is issues with something called IPP, incidental parameters problem. Okay, and we're not going to go into a lot of the details in terms of theory, but basically just noting that it is an issue in those types of models in terms of categorical. I think I only focus on the categorical for now because there's just so many different realms for different other limited dependent variables. But it's just I want to show it in the linear setting first, and then it makes it a lot easier when we're thinking about the nonlinear models. We're going to do a little bit of showing a little bit of difference in difference. Just, you know, a way of thinking about methods of trying to get a causal outcome and the best circumstances. And then I'm just going to talk about these quantile regressions again. I'm basically just kind of bringing in some information that I'm going to kind of use from the correlated randoms effects or other methods of dealing with the unobserved heterogeneity. Okay, so this is sort of how we're going to set it up today. And then that's where mine will end, and then Blessing will take the last session. Okay? Is there any questions before we begin? Okay. Like I said, I do know that all the stuff I sent last night is a little bit hectic. So if you are in that area and you do have a question from the code that I sent because you're using it for something, just because I know you probably couldn't look at it all last night, you can email me because, like I said, this will be my last day. But if you have questions on it comes up, even after the class finishes, send me an email. Now, if you have my code and you're asking specifics about it, I can try to help you out with it. Okay? Because I was going to try to cover it this morning, but we were a little late, so I didn't want to take up more time with that. Okay? So yeah, don't be afraid to send it to me, especially if it's something you're using. I want you to be able to know what it's doing. Okay, so for the reason we're calling this sort of big N panels, we're thinking more along the lines of big N, small t. Okay, thinking, you know, we have, and big N in this case can be a couple of hundred, but we're just thinking that we only have a few years of observations. This is typically where we have a little bit of issues with IPP or sometimes if you're thinking about nickel bias or any of those. So at those times, we just want to kind of give an idea of what we can do versus what might not be exactly the best thing to do. Okay, so we're going to combine cross-sectional data. So we're thinking about the I dimension. And we're going to, with time series data on the t dimension. So we're going to track the same units over time through repeated sampling. And so this may be unbalanced due to attrition, units dropping out. We do have ways of making adjustments. We don't really go into those too much here in terms of that, but there are weighting strategies that allow for you to sort of rebalance the weights within your panel. Inverse probability weighting is one of those. There's a few more that I can't think of right now. Regression adjusted, I think. But there's options out there just in case you are worried about that. Okay, so why short panels? Estimating each period separately risk omitted variable bias. So a lot of the things that we actually try to look at, we assume that in the cross section, you know, 1 year is very specific, to the day that model, and nothing else is influencing it. But as we have more basically cross sections coming in, we're going to find that there is some type of persistence. There is some types of relationships. We find this in trade a lot. Those pairs of countries that traded a lot before are going to trade a lot next year. those countries that trade a lot are more likely to actually form free trade agreements. These are all things that basically there's a relationship there that's pre-existing that we sort of have to deal with, but we can't really observe it as much. We can observe these economic outcomes, but there's some other underlying things that we can't see. Okay, so if we did it in a cross-section, we'd be missing out on maybe previous outcomes or future that are just connected in some way, some type of persistence. And then we can also think about things that change slowly over time, health outcomes. It's not like you just all of a sudden wake up and you're better in terms of chronic illness or other things. If you visit the doctor on a regular basis in a prior year, basically the next year might be the same. There's all these things that we have to sort of deal with. I got it.
Thank you.
Yep. Okay, so in this case, we just need to capture in some way these trends, or in some ways, we're going to actually use them to find and remove things that basically are slow moving over time. Okay? Cross-section across time. So we're going to combine independently sample cross-sections and evaluate events or policies. One of the things that actually helps us out here is that basically larger sample sizes, higher precision and power. Okay? That's good for us. But it assumes consistent measurements of the variables over time. So to give you an idea, if I was trying to look at trade over the last 5 years, that would probably be the worst time to sort of look at this. We had so many different events coming in that basically it was an unusual outcome. So in some ways, yeah, values would not be changing, right? Those would be consistent over time. But if I was trying to measure some type of policies, you know, a free trade agreement a few years ago would be very different from yesterday, you know, because those policies sort of went out the door. So consistently measured, I'm not sure how you could do that with, you know, these events that are happening right now. Later on, we could use varied techniques to sort of measure some type of unique events within that year and then, you know, control for it. But at the same time, that would be still some way of trying to keep consistency in our defined measure of free trade agreements or certain policies. So that's why we need to make sure there's some consistency as well there. That's why typically if we have very long panels, we typically will try to say, you know, during this time, you know, these were sort of the events that were happening. We need to sort of keep those in mind for whenever we see extreme cases of increases or decreases in our estimates. So these are all things that we need to sort of consider. For now, we're going to just assume that we have a consistent type variable that we're following. Okay, and that basically nobody's making huge explosive type changes. You know, we're thinking in that sort of framework. Sorry, news has been in my head recently about all this stuff. So, okay, so and in terms of endogeneity, so just recall that using additional covariates help to isolate this relationship between the variable of interest and our outcome. That's why we have these controls. And by doing this, if we can isolate it, then good for us under perfect conditions. But a usual problem that we have here is unobserved outcomes. So basically in applied work, this is our arch nemesis here. Basically endogeneity. There's something in the error term that we can't measure, we can't observe, and that most likely is correlated with our other controls. Okay? What's the likelihood if we're measuring something that we don't observe ends up in the error term, but it somehow is not correlated with the other things that we're using to measure y? Not very likely. All right? It's most likely there is some correlation. So I'm going to focus on the omitted variable bias, but we also have selection. I've already sort of talked about that in the sense that, first come, first serve. Who's the one going to be in front for any type of work program or something that is related to, how much time you have available. Or in your case, we showed an example where we actually logged it and threw out everybody that was working. That is selection on our part by doing that. We've thrown out a portion of the population that we thought didn't matter. That's problematic. But it is often related in some ways to omitted variable bias, so I can kind of put those together. The ones I'm not going to really refer to too much is reverse causality and measurement error, but they all fit into the same thing. That basically there's some type of process that we can observe that's causing the issue where we have the relationship between the error term and the other right-hand side variables. Okay? So these unobserved variables, that's not proper way to write that. Unobserved variables or variables, I don't know why I wrote it that way, that we want to control for but have no accurate way to measure. So we're thinking about ability or motivation, or in this case, I'm just thinking about work or in terms of education or something else. In terms of motivation, we think about the differences in individuals' motivation can affect both their educational attainment and their wages. I can see you running around most of the time. That could help me figure out your motivation. But in some ways related to that is your overall ability as well. You could be running around but doing nothing. Or you could be running around with your ability and doing a lot. Right? There's a lot of things that I can observe. I don't know, I've always seen that joke where, you have somebody in an office, but when you go by the boss, you're always running. The rest of the time, you're just, strolling around, but if you go by the boss's office with the glass windows, you run by. So things like that, it's those unobserved things that we have to keep in mind. So just recall, these are the factors that we typically use. We have our yi, t now, so we're throwing in the t, just so that we have that panel dimension. We have our usual controls, but we have this new AI term, and I'm apologizing because I have a bad tendency of jumping between AI notation and CI. Just keep that in mind that sometimes it shows up as CI or AI. But basically it's just meant to be unobserved to the econometrician. It's something unique to the unit of analysis. And because we don't control for it, it ends up in this error term. This becomes the composite error term here. Okay, so causal inference basically requires us to find a way to control for the AI that's unobserved or can't measure if we want strict exogeneity to hold. When I mean this, I mean if there is some type of relationship or correlation between AI and the other right-hand side variables, this is problematic for us. We need to figure out how to control, or at least mitigate the problems related to that. If there is no relationship, which is an assumption that people do make whenever they sometimes run OLS with, say, random effects, basically you're making the assumption that there is no problem between having this in the error term because it's not related to the right-hand side variables. And then we just sort of lose, we have a higher error variance in that case. Okay? But we're always going to assume right now, for the stuff we're doing, that basically there is some type of relationship, or we're suspecting that there's some type of relationship. Okay? So just keep that in your mindset. That's how we're going to sort of kind of go through today. So a lot of times the point that we usually start off with is fixed effects. But I'm going to start off with first differencing instead. Okay? We'll kind of get into the reasons a little bit why. But so with first differencing, basically we can set up the model as we did before. I've only done one extra control, in this case XIT. And so it's very simplified and only 2 periods. So remember that we're assuming that the AI term is in the error term, and it's unobserved, and we're going to assume for now that it is time invariant. Okay. Now there is some newer research that says, you know, that basically we can do we can look at unobserved time variant heterogeneity as well, if under some certain conditions. We're not doing that here, but like I said, this stuff is always expanding a little bit. But either we assume that the AI is time invariant, or we assume in some ways it's changing very slowly. Okay? So we can actually write these 2 periods out as 2 equations. Remember before I said if we estimate an equation for one versus the other, we actually could be causing omitted variable bias just by doing that. So in this case, we want to try to estimate these 2 together. But we're going to make a change before we actually try to estimate. What we're going to do is write it out as YIT and YI2 and YI1. And by writing it out in this way, then basically we can subtract one from the other. All right. There is a little modification I do by just representation purposes, basically, so I can keep the constant. Because if I had one that's beta naught and one that's beta naught, I'd lose the constants. Typically, we don't like running models without constants. Okay, just keep that in mind. So that's why there's just this little reformulation of the structure of the second constant, so that when we take the difference of these 2 by yi2 minus yi1, we formulate a new equation. Basically, the delta yi is equal to delta naught, the addition to the constant in the second equation, beta 1 delta xi delta ui. Okay. Basically, all this is trying to tell you is that instead of actually running the model as is, we're going to basically take the difference between the dependent variables and the independent variables. When you do that, that implicitly takes the difference of the error term. Okay? Because remember what it is, what the error term is basically. Okay? We could reformulate this to where it's basically u is equal to this equation minus the yi. Or we could actually put it the other way. Ui is equal to the difference in yi minus delta naught and beta 1 delta xi. Okay? So the key assumption here is that basically delta xi and delta ui, there is no relationship. There's no, in some ways, it ensures basically that when we remove, or basically ensures that differencing removes the individual effect of ui. So basically we have no serial correlation over time. There's no relationship between the 2. Okay? It's another version of the strict isogeneity. And it should hold even as we increase the number of t. But since you are a time series, you sort of know that basically as we increase the number of t, we'd have a little bit of issue with serial correlation and the error term. Okay? So you can keep that in your head for now, for that. But so this is basically the way we would do first differencing. And we also treat this exactly as we did before. We don't talk about it in terms of the difference, 1 unit difference in x is equal to, or this is the effect. We talk about it as a 1 unit change in x this would be the effect on yi. Okay? Problems that we actually face with doing this is basically differencing reduces variation in most cases. Now, note that I said in most cases, doesn't mean all cases. both the dependent and independent variables. Okay? If the variable has a little variation before differencing, this method causes a lot of issues. Okay? You're basically estimating something that's only changing by 0.0001 because it's not changing very much over time is problematic. And what about things that are time invariant? I've shown a lot of examples that are dealing with wages. We're talking about people that have already been through school, 25 years of age and higher most time. Their education's not changing. If I care about education, I can't use these methods. I've lost my variable of interest, right? Sort of. So a lot of times we'll do possible little tricks that allow us to keep these things in there. One of those I probably wouldn't advise with differencing, but the other methods we'll show later on in terms of interactions help us keep in time invariant variables in there. From my memory, I don't remember it being very good to do those interactions in differencing, but I could be wrong. We have larger standard errors anytime we have less variation. Okay? Also problematic. If the variable that we're interested in no longer significant, we can't say anything about inference with it. Again, we don't want to kill our research, so again, we have to figure out ways of dealing with that. Or change our methods. So basically this is potentially limiting the ability to draw conclusions about the variable of interest. The only reason I'm trying to bring this up is that a lot of times that people in some research areas have used indexes that are slow moving over time. I mean slow. If that's the case, then you're trying to use this type of method and difference it out. You most likely are getting some type of spurious results, right? Because you've basically cut something down that was only moving by 0.01 over those years, and then all of a sudden you difference it. It's not going to be very good in terms of the overall effect or the overall measurements. So you just have to keep that in mind that those types of methods can basically cause havoc within your models. Okay. When you have two or more periods, or more than two periods, difference error terms may become serial correlated. So that's where that issue, we would need to make some adjustments. So in panels with large N and small t, clustering center errors by the cross-sectional unit can help adjust for serial correlation and heteroscedasticity. And I'm just saying can help. There are many different methods that you can actually attempt to make further adjustments, and a lot of times it's not just about clustering on the standard error sometime or clustering the unit of analysis. Now we have additional methods that look at two-way clustering. Sometimes it's not just about the unit of analysis, sometimes it's about how over time. So we actually have made adjustments for those types of things to try to improve that. Possible solutions, I always like putting this and then saying, increase the number of cross-sections because first difference strategy can be extended to n cross-sections. Great. But if that was an option, why didn't you do it before? So it's sort of like, you're saying to do this, but at the same time, if that was an obvious thing, you would have already done it, most likely. Okay, so I put it there, but at the same time, I know that most likely you've already added as many of the cross-sections as possible, okay? The other one that you could do, the longer you get with t, and the problem, remember we were talking about these things are slow moving over time, we could take bigger differences. And there is some literature that actually focus on that basically economic data that we have is changing, but it's not speedy, right? So you're trying to measure something that's moving very slowly over time, and then basically doing it with a lot of different cross sections, but your model might not be able to pick up those changes very much because it's doing it so quickly. So a lot of times we might space out even in terms of panels and using fixed effects, we might actually space out and take it at 5-year intervals. That gives us time to pick up those differences. Okay? It also gives a lot more time to get those bigger changes, and we might not reduce the amount of variation as much. Okay? So we use this in trade. There has been some papers recently that show it doesn't really matter anymore because of all the fixed effects we use for international trade. But there was a thing that we still use and a lot of people still advocate for, which is taking every 5 years or every 3 years to give those outcomes time to change. Okay? So these are possible ways of dealing with that as well, especially if your variable is, you know, like an index or something. Okay? So just keep that in mind of ways we can make adjustments. And I just wanted to give you an idea of what I mean by this. So basically, this is from the, what is this from? And it's from the wage panel data. And I just wanted to show you what it sort of looks like. So before we actually difference, basically this would be how education looks across our sample. If this was actually real and not, it should actually not show anything. Basically after I difference, because I'm looking at people that are already out of school, it's gone. Everything is 0. Makes no sense to use this method particularly for that type of outcome. The reason I'm showing this in terms of hours is because this data set was at a particular time where you had people that were working in 1 year, not working, or not working and then started working. Because of that, when we're looking at it, this would be before differencing, and this would be after differencing. Even though there's some long right tails going, right and left tails here, if you want to do the calculation, there's actually more variation after the difference. That's why I meant that it can happen, but it doesn't mean it always happens. When you have staggered data like that, especially for unemployment, working hours, you have huge differences between 1 year. 1 year's a good year, 1 year's a bad year, and so forth, especially during bad economic times. Okay? So in that case, you still can get the amount of variation or better variation. So just keep that in mind too. It's not always the case. The next one that we have, I know that y'all are all familiar with that, is fixed effects. Yeah.
Okay. So what I want to understand is if I conduct first difference, the main goal could be to achieve mean stationary data, and if you not the stationary or first different, you always do the second different. You want to see certain clean trends, either uptrend, construction trend, or downtrend.
Let me go get the
first difference, and if it's not stationary, then I go for second. It's fine to understand that.
I can go get the time series person. That is one of the methods that people do use for that stationarity stuff. Is because of my field, we don't really deal with that as much, but it is one of the things I know that they do it for. And yeah, you could do it for that. But when we're thinking about that as well, it's also a lot of times about the error term. We're thinking about that serial correlation as well. So from my side, I'm thinking about the error term, but I know from the time series side, they're thinking about the fact of those trends that are forming in those variables and trying to get that stationarity. Well, it's stationarity across all variables, but they might have to difference again to get another variable that was not stationary. And those methods, I don't keep track of those as much. Yeah. You should ask Steve that. I'd like to see how he responds. I was thinking about the last time he actually dealt with the time series as well. Me and him, we just don't deal with it as much because we're over mostly in the either we're in very large panel settings or we're in cross-section settings. So we don't deal with those issues as much, or at least our area of research does not. Whether that's a good thing or not, I'm not so sure. Okay, so I just want to put that out there because they got me on camera here. So. Gotta cover myself just as much as possible. Okay, so in terms of fixed effects, again, it is all about getting rid of the AI. How did I call it? Yeah, I called it AI here. In this case, by the way, the reason I was trying to change AI recently is I was talking about the same type of thing, and I kept saying AI, and they were thinking, yeah. So that's where I started trying to switch all my notes to CI to get away from that. So yeah, AI in this case is still within the results, or was still within the equation. And we want to try to remove it this time, but we want to do a within a transformation, or I might, instead of saying within most time, I'll probably say demeaned approach. So in this case, we're going to demean all our dependent and independent variables. And yes, I did show it here as removing the constant, but there, we always include a constant, so just note that it's in there. I could have changed notation to show it, but I'm just going to leave it there for now. In this case, we're just going to take the mean across I, and then for the dependent variable, and then subtract off or demean that outcome. And we do the same thing for our right-hand side variables, and then that implicitly takes the difference within the error term. The good thing about doing it that way is that basically we remove an AI term. The average of the AI term, because there is no variation across T, is removed. Now remember, if we were thinking about this in terms of slow moving, there might be something here that wouldn't be exactly equal to 0. Just keep that in mind. So we think about this as being equivalent, because sometimes we'll talk about this. Sometimes you'll see in the literature that basically they just run a least squares dummy variable model. Those two models are mostly, you could say, equivalent in how they're trying to remove the AI term. There are some things that we need to keep track of, though, if you're going to consider them to be equivalent. So both methods are controlling for the unobserved individual specific heterogeneity. Okay? Same goal. All the methods we've shown so far had the same goal. The problem, though, is as we get larger and larger, and think, okay, so when I start off with 100 individuals, and I want to do the dummy variable approach, n minus 1, 99. Think about as that increases. To give you an example, and just using aggregate bilateral data for trade, my unit of observation is pair. I have 32,000 possible pairs. 31,999 dummy variables. No program can deal with that. The programs that you're using, even the most technical ones, are usually limited to, around 10 to 11,000 size matrix. Okay, we do have techniques to get around that nowadays. So I'm not saying they don't have techniques to deal with that, but if you're going to actually try to put in all those dummy variables, then you would be implicitly putting them into your equations, which then your computer has to handle, and it can't handle that. Okay, so that's where it basically becomes very impractical as n gets very big. Okay, so in short panels, usually the only thing we have to sort of deal with is the incidental parameters. So we might have a large n, and here I'm just thinking about a couple of hundred. But because t is so short, remember that is having to estimate each of those, right? And as we have our n fixed and our t being, n being fixed and and t is allowed to increase, basically we think about these as being nuisance parameters, or what do you got? Well, they're parameters that are not the main goal of our regressions. But what happens is, because the program is trying to estimate these, we actually get inconsistent estimates in the parameters. So basically, estimates of the AI term, which is each of these n's is sort of the AI term. Basically, are inconsistent due to the inefficient observations per unit. So I have one unit, but I only observe them for a few years. Okay, and from that, because we're trying to estimate the effects related to each of these, it's actually going to cause issues in the parameters that we don't care about as much, but because of inconsistency in these estimates, lead to inconsistencies in the other estimates. Okay, so it's like a knock-on effect. Another name they sometimes give to it, if I remember right, is a smearing effect. Basically, basically our inability to estimate have a consistent estimate of the incidental parameters leads to bias in the other parameters. Okay. So a lot of times this is where we have a little bit of issues, including this dummy variable approach. But in the linear model setting, it's not as much of an issue. Okay, so for now, I'm only mentioning it here that it becomes a little bit of an issue, but most likely it's not going to affect the consistency of beta in these linear models. They're not going to be, those dummy variables might be inconsistently estimated, but technically we're not going to get much of a problem in the variables of interest. This is going to be a bigger issue when we get to the other models that don't handle these types of inclusions as well, because it's using some type of MLE type approach or GLM approach. Okay? So this is why, the reason I'm bringing this up is just so later on we're going to see what happens when we actually do this, say, for a logit model. So we're going to kind of look at the incidental parameter problem. Okay, so that's the fixed effects. So additional on the fixed effects. Basically, I've already said that in models that include dummy variables for 2 time periods, oh, sorry, this is actually a little bit different. A lot of times what I haven't mentioned so far is that in these models, remember that, that additional thing that I put on terms of the constant? I didn't mention at the time, but we could have considered that a dummy variable for the year, right? We basically use a dummy variable that represents the second year, but not the first. Remember, because of that that dummy variable addition, basically it's going to be like an adjustment to the constant. So when we difference it out, the dummy variable for that second year became the constant. Well, we could do that similarly in the fixed effects, because there is 2 ways that we can actually get variation across the individual, but there's also unique events within the year itself. Okay, so in this case we could actually include a dummy variable for time. So in a 2-period panel, this would be a dummy variable. If year 2, 1. If year 1, if year 2, 1. If year 1, 0. Okay, and it's just a way of marking the average effect within that year for the population within your sample. Okay, we do this for a lot of times for especially in trade that basically mark bad years. You know, this helps if there was a global recession that year. All the countries on average are affected in some way, but that should be different than the unique unobserved heterogeneity for the particular country. So we're getting a global average effect, and we're getting we're kind of looking at the individual effect as well. So a lot of times you also want to include a year dummy in there as well. It's not just unobserved heterogeneity, and you don't really care about the year dummy. Now, when I used to teach this in Stata, I just want to, I guess I'll put it here too, because some of you do use Stata. Do you use the xtreg command? Sometimes? Yeah, you do or don't? I know some of you use Stata because y'all have asked me questions on it. Okay, so if you do, when you actually do the xt set in there, note that it's only going to control for the unobserved heterogeneity of the individual. If you actually want to include a time fixed effects, or a time dummy if you call it, then you would actually need to include that in the model yourself. Okay? A lot of times it's only doing one dimension, not both. Okay? Just keep that in mind if you do continuous Stata. In terms of being time invariant and uniformly changing variables, FE cannot identify the effects or the effect of variables that do not vary over time. We've already said that with the first differencing. But this is where we actually can maybe do something about that. So a lot of times there are variables that we want to control for the unobserved heterogeneity, but we really care about something about the individual. You know, in terms of development, sometimes if they get a particular vaccine or something, if we want to continue to see how they might change over time, if we were to use these types of methods and we can follow them, we would lose that. So what can we do? Well, we could actually try to interact it with something that does vary over time. Okay? A lot of times what I've seen people do is actually interact these with, say, the year dummies. It has to change because the years are changing. And that would actually give us an aspect of how, whatever our dependent variable is, what's going on over time. Okay? We have other ones that I've dealt with in terms of, we were looking at ruggedness of the terrain on health outcomes of children. Ruggedness doesn't change. We were having difficulty with that. So we could actually interact it with a variable that is changing over time in our population. So these are ways of keeping this in. It's not the exact way we would want to do it. We're not isolating it as much, but it is better than it being dropped in this case. Okay? So it also can't separate out the effects of changes or a change that is uniform for everyone. If you're following people perfectly, and we're looking at age, well, everyone age in that sample is moving by 1. That's usually not a good thing that we want to sort of look at, right? But if it's something like experience, here I kind of give an idea that, you know, experience increasing by 1 for each period is bad. But what if it's actually sporadic? You know, some people are working sometimes they're not. So then everybody's isn't changing by 1. Then I might be able to pick out some information. But if say that 99% of you in my sample are all moving by 1, I wouldn't be able to do it. But if I actually have some unemployment, I'm following several years, then say about half the sample isn't always increasing over time, I could pick it up. So these things that we can basically pick out, but if within the population, if everybody's moving exactly by 1, or even by some type of constant, then that would be problematic in any type of estimation for us. Okay? And this also applies in terms of the first differencing, right? If we take the first difference and everybody's increasing by 1, then our change in that variable is 1, which is a constant. We have a constant in our model already. So these are things that we do have to keep track of in terms of our variables and knowing exactly what's going on. Okay? We need to know, you know, what's the movement? How much variation do we have in these? If I choose to use one of these methods, does it actually, you know, take something that was huge variation across the population and it move it down to something that is, you know, very small? These are all things that we have to keep track of. It's not just throwing them into the models and running them. Okay? We still assume strict exogeneity. And the only reason we can assume this basically is because once we remove the AI term, if that is our nuisance parameter in this case, then hopefully we would have strict exogeneity. So we basically in FE allow the individual effect AI to be arbitrarily correlated with the XI. We say it that way because once we demean, and if we do a good job of it, that thing is gone. So there's no arbitrary correlation anymore. Heteroscedasticity and serial correlation. So in short panels, we also suffer from heteroscedasticity. There are some things that, it's very similar to the techniques we've already sort of seen. We've focused on clustering, bootstrapping, whatever methods that are particularly used in that field. We also sometimes have the autocorrelation and cross-sectional dependence. And basically, this is where, so in this case, we do have bias standard errors, and we sometimes use techniques to adjust for those for our inference. Okay? It's not something we should just get, not even care about. But overemphasis on those can be problematic. Okay? And I'm just saying this morning, I think I've already told a few people that were asking me about something that I had, a student that basically focused heavily on one thing, standard errors, for a very long time. But it didn't change the overall question or what was coming out of the model. Okay? So we do try to make the best job possible in terms of adjusting for the standard errors for any of these reasons what here. But we should stick to what the literature is doing. Follow the other literature, or the literature within your field, and methods that are coming out, but don't go overboard on it. And this is in my personal opinion. He just spent too much time because it didn't change the overall concept of the results. Everything was still there. The only thing it really added was one additional star. That's too much time for one additional, if you want to say, one additional star is the best way to say it. So just keep that in mind, that basically we do this, but don't go all out on this. And there are like several techniques that we deal with this. Okay, efficiency considerations. Basically, FE typically, I'm just again covering myself, typically yields more precise estimates than FD, especially when the idiosyncratic errors are serially uncorrelated. But you're coming from time series and you're going to fight me on that. So, again, follow the field that you're in. Also, there is a few tests that you can run for this in terms of testing first differencing versus fixed effects versus random effects. Again, that's up to you to use, and there are some fields that still do that. But in general, and especially in international trade and development, that from where I'm at, most time first fixed effects always wins in those types of small little tests. Okay? So again, that's my preference, but it doesn't mean it is always the right way to do it. Stick with what's in your field. But FD, or first differencing, might be preferred in the differenced errors are correlated over time, and you know this. Okay. The reason why I wanted to show the method that comes after this is because a lot of you are used to using something called, if you're using these methods, you use something called the Hosman test. Okay. Yes, there's some general ways of doing that, but there are ways to do more regression-based type checks. Okay, so in the one I'm going to show you in a second, it's one of the ways of actually doing something similar to the Hosman test, and we'll just sort of, talks about it and everything. And the reason why I like to show it here is because actually when it comes to using these in my logit models, in my quantile models, any of those. This is a technique that allows me to hopefully overcome the IPP problem that we have in those models. So that's why it's easier to show in the linear case, and then when we move on to the nonlinear, we can talk about it there. At least I think it's next. Yeah. So this one is the correlated random effects model. So we talked about it in terms of first differencing, that basically we can try to difference out the equations. In terms of fixed effects, and we can try to demean or do a within transformation, or we can try to model it. Why not try, if we know something about the unobserved, we can't see it, but we know there's some relationships, then why not try to model the AI equal to the means of each of the right-hand side covariates that do vary over time? In some ways, it's a very similar strategy to what we had prior, because if we actually, so in this case where the AI here is decomposed into this equation that has its own error term, in some ways, so it's only related to the time averages of our time varying right-hand side variables. And we're going to assume that the Ri term is uncorrelated with the regressors. Okay? If we actually substitute this back in, so we take this and put it back into there, we come up with this particular equation, which leads to a different error term or composite error term. But remember, we assumed that this Ri term was uncorrelated with the other regressors. But now that we have it here, remember how we did the demeaning approach? That, or sorry, in this case, beta 1 xi t1. What if we were able to put these two together and we were thinking about this as being you know, have parentheses around it, it would look very similar to that demeaning approach, right? Except, you know, what we're going to do is we're actually going to estimate this, both of these parameters. But again, like I said, it does have that same type of conceptual type equation. Okay. Well, it ends up being, in most conditions, there are a few times it might not be true, it becomes equivalent that the random effects model, so if we use this and we run a random effects model, the only reason we're using RE instead of the OLS in this case is because of the structure of this error term, we have to make an adjustment to the standard errors. But if we do that, we find the beta on the CRE is equal to the beta on the fixed effects. Okay? So remember before, we killed off the AI term by basically demeaning, which might lower the amount of variation we have here. Here we're keeping the amount of variation we had before, but we're just using the means to account for the AI term. Okay? So basically what this tells us is by doing this approach, we have something that's equivalent to a fixed effects. But we're not demeaning, so what else does that mean? If this had education there, stays in. Health or gender stays in. We're not demeaning, so those things stay in the model. We did not lose the time invariant variables. That can be good for us as well, especially if we care about them. Okay, so basically by doing this, we get equivalent of the fixed effects estimator. We get to keep the variables that are time invariant. And we can actually do a test, because we ran this particular model and we're actually doing all estimates for the coefficients on these mean outcomes. We could actually do a joint test here and find out, does the mean effect, is it jointly significant? If it is, it actually means that fixed effects most likely is the proper manner of doing this process. If it's not, random effects is most likely the proper way of doing this. It actually works in a very similar way to the Hosman test. Okay? So the advantage of this is we include the ability to test the validity of the fixed effects by doing a joint test on these coefficients that they're all equal when they're all equal to 0. And by doing that, we can basically test that fixed effect assumption. Because if you look at the random effects model, what it actually is doing is you're trying to estimate some lambda on those particular unobserved effects. If the lambda is equal to 1, you're back in the fixed effects realm. If it's 0, basically it's basically meaning that there's no relationship between the error term and the right-hand side variables, and you can just make the assumption that they're not there, or is that it's not important. Okay? And all you need to do is make an adjustment on the standard errors. But the biggest thing that I like is basically the fact that permits the inclusion of time-invariant regressors. Remember that we want to do the best job we can with knowing how education is going to affect wages. In a panel, that becomes difficult. Using this, it allows me to keep it in and keep my question still the same. How much does education affect my wages? That's where I see the most benefit for this from my side. Okay. Okay, I'll save the example since we're close to the break. But is there any questions so far? Now, remember, I know that most of you have seen this. It's just trying to give a refresher on how we think about the first differencing, the within transformation. I know I skipped random effects. It's just not something that's typically... Basically, the assumption is that there's no relationship between the composite error term and the right-hand side. So basically, the only thing we're doing is adjusting the standard errors. That's why I don't bother with it. So is there any other questions about these? Because I know it's just a refresher, sort of. And, oh, sorry, yes.
So on slide number 20.
On which one? 3?
1, 3.
Yeah. That one?
So, yes. So on point number 2, or 1.2. So when I run the fixed frequency model, just initially like that, meaning that if I have a variable of gender, put it all in 2, basically, I'm not really getting anything from the result.
It'll fall out of the model. So because it's constant, it's always either 1 or 0, then basically it will follow the model because it's never changing. So when you demean, basically you're not changing from 1 to the next, so it becomes 0, and then it's removed from the model, just like the AI term.
Meaning, prefer everything continuous.
Well, it's not that we prefer it, it's that it has to be. Because we have a preference for knowing things that don't change, that are constant about characteristics of individuals. We'd like to measure them. But if we use that method, we are shooting ourselves in the foot, basically. If that's our primary variable, we have to choose another primary variable. Or we have to come up with other strategies. So to give you an idea, so there's a very good example, if I'm remembering correctly, in Wooldridge, that basically shows, okay, we're looking at, what was it? It was it gender or, I'm forgetting the variable, that whatever it was time invariant. And what we did was instead was he basically interacted those with the year dummies. Okay? And what it's giving is the effects of being female and as the years are changing. Because the dummy variables are changing and the interaction allows for that change, then it doesn't become time invariant anymore. It's actually changing. Okay, so we have to come up with little tricks that allow us to pull out that information for the variables that are not changing. And I mean, there's been a lot of good work in that side as well, trying to, you know, it helps us pull out that information. It does add a little complexity in, you know, what is just the effect of gender, because now it's sort of intertwined with the years as they go along. Or if we intertwine it with something else that is continuous within the data set, then, you know, they're sort of intertwined now. That's why we have to be a little bit more careful in our interpretations. Okay? Okay, so we'll take a break. Come back at 10:30.